Yes, so welcome all to another Scientific Computing Club meeting. This week we have a workshop on CMAKE, and of course, like always, we have our trivia. So we'll start with our trivia. Okay, now on to our workshop. So we're going to be talking about CMAKE today. Just the basics, though. We're not going to get into anything complex. Going to get. Hopefully, this is accessible to anyone who is familiar with C++ and compiled languages in general. So let me just make sure I'm sharing the right screen, and we'll get started. Okay, so there's the difference between interpreted and compiled languages, and this is the difference stems from how you go from the code that you write into how it becomes understandable to the computer. So ones and zeros, how it becomes a binary file. So there is a simple way that this can happen, where like what's simple to you, where you take your program that's written in like C, C++, or some other compiled language, and you just get your compiler and you run a line that says like if you're using like GNU compiler, you like GCC, and then you type in the name of your script, and then it generates a program. But in the background, more stuff than that is happening. And then once you get into more complex projects, the process can become even harder. So additional steps are added in to make this all a little more organized. So what exactly happens when you're compiling, when you run your compiler, such as like GCC, is compiling and linking happens. But for more complex projects that involve multiple, not just one, not just one file like we have here, there's multiple files that happen. You want to configure how all those files are found, for example, and then what compiler you're going to use potentially. And then after the configuring is done, after you determine what like different kinds of programs you have in your computer, then you can go through compiling and linking. And then this whole process here, actually, you could refer to as like a tool chain for like a particular software. Then afterwards, you can also do some testing and then install whatever you've made, whether it's a executable or a library, into a certain location. So this is the general process of like how a compiled language works. Either it can be like a simple process where you're just compiling, or you can go through this whole longer process, which is usually used for more complex projects. So the configure step is where CMake comes into play, and it can also be used for other things like building or installing or compiling. But the main part of it is for configuring. And so what you can do when you configure is you can change which software you're using. So you can change whether you're using the BLOS library or OpenBLOS library. So BLOS is a library that I think it was written in Fortran that basically tells you or gives you functions that can do like matrix multiplication very fast. And OpenBLOS is a faster version of BLOS. That's why it has all these flames on it. And so one thing you do with configuring is say, I want to use OpenBLOS instead of BLOS. And then you can also change compiler options and also say like where the software is going to be installed once the whole compiling and the whole process is complete. So the configuration software is going to be control of these, and that's what we want. And so what you would give as an input to CMake is like file paths for if you have like a certain library and location, you give it the file path for that. And then also what build version of your software that you're going to do. And typically what CMake will produce, just CMake by itself, not like the build software of CMake, is it'll produce a makefile, especially if you're on Linux or Mac. This is the sort of end result of CMake. And then this is another sort of part of the compile link process where you would run this make file and it would do the building, the actual compiling linking project. On Windows computers, it can be different because you can run it basically does it through Visual Studio, and Visual Studio has its own like environment. Actually, I think that's what this next slide is. Yeah. So yeah, so for CMake, it's going to make files on Linux and Mac, but for Windows, it's going to do a lot of stuff through Visual Studio. So the process is going to look a little bit different. And we're going to see some of the differences between those today. So that is a little bit of an introduction, and now we'll get into the actual workshop itself. So we're going to first go to the documents repository and check out a sort of a document you can use to follow along with this workshop. So we just go to this address. Can I hide this? So yeah, sc2umich.github.io documents. And then you can go into the workshops tab, and under summer 2024, the second meeting too, there's a guide. And this is the guide that we're going to be going through. And also, I have, if you can go through this guide kind of from scratch, but it's also part of this repository, all the files that we're going to be using. So if you want to clone this repository, all the files will be there already made for you. And you can find the repository at GitHub too, but it's under a different address. So we'll just show that really quickly as well. So this is the address of the GitHub repository you can clone. And so I'll be working in this today. Any questions on like the compiling or like the whole process of configuring anything like that? Or the usefulness of configuring?
I'm pretty unfamiliar with it, so I would mostly just have to take your word for it.
Okay. Yeah, it might be a little bit more useful. Like it's kind of, I guess I kind of spoke about it abstractly. So once we get into the examples, it'll become more useful. And we actually have one example at the very beginning that I think is going to be illustrative. Yeah, so the prerequisites for this are to, of course, install CMake because that's what we're going to be going over. Installing Git is good if you want to clone this repository. You don't need Git, but it makes it easier. If you want to download it without Git, you can just download the zip of this repository and extract it. And then having a C++ compiler. So if you're on Windows, which you use Linux, right, Sam?
Yep.
Yeah, so you're already good on a compiler probably. Because if you're on Windows, the Windows defaults to using like Visual Studio, Visual Studio's compiler, and it's hard to use that from the command line like we're going to be doing. They usually want you to do it within their like environment. It's possible, but it just takes a few more steps. And there's some like good emulators of like what is used on Linux, which is most often time like the GNU compiler. And if you this web 64 dev kit is like the compiler that is on most Linux machines built for Windows machines. So that's what I'll be using for um, a lot of what we're doing today. All right, so we'll go on from part zero and into part one. So before we even start working with doing our own stuff in CMake, we're going to look at someone else's CMake. So one of the projects that we're working on currently in the club is a Python project that's incorporating Blender for visualization. And one of the first things we have to do is in order to incorporate Blender in Python by itself, you have to recompile it as a Python module instead of as like a standalone application. And so the way that you change it from being an application that you'd like double click on your desktop and it opens up is through CMake. Before you even start to compile it, you say like, I want this to be a Python module instead of an application. And so this is Blender's like own sort of like GitHub, and they have, this is all their source code. And so one thing you can see right in the very beginning of their directory structure is this CMake list.txt. And so this is kind of their program of how many different ways you configure it. And we won't go through this in detail because it's very long, but you can like see the amount of detail that would go into specifying all the different ways you can build it. And so when you might want to get really into this sort of thing is if you were going to make your own modifications to Blender, since it is an open source project. You might want to change some of how this is configured. But this is a very, very long document, and there's a lot of settings that can be changed in here, and to change how the program will be made in the long run. But for this next part, we'll actually go to the Blender website and where it talks about building it as a Python module. So this is like, yeah, just part of their documentation on like how to install Blender if you want to do it in a different way or want to change the configuration at all. And it actually has, if you go to like the Linux part, it tells you about the different things you can configure. So down here at the bottom, it has manual CMake setup and goes into a little bit about the different things that you can change on it. I'm trying to see, they had build options. So there's many build options, and they go into the different things that you can change. So you can change it to where Blender only runs on the command line, and you pass it certain commands to generate your images or animations, things like that. And then what we're interested in is this Blender, this BPy thing. That's the name for their Python module. So we're not going to actually build and compile it because it takes a long time, but we'll look at like what that sort of looks like. And then then down here, set up for developers. So if you're going to work on Blender, you would want to know and make Blender usable on like other platforms. I think that's what Xcode is for. And so to do this thing to make the Blender Python module, they make it really nice for you. And so instead of typing in a bunch of commands into CMake to set up the configuration, they already provide a configuration file for you. So they're calling the CMake command, and then they're passing this -c argument, and that's going to give it the certain configuration, changes all the settings of the compilation to make it to where it would make, when you compile it, it would actually make the Blender Python module. And then it talks about some other stuff later that you would need to do to actually use it as a Python module. But yeah, well, I'll kind of show you guys what this would look like. So we'll first go, say you're in your home directory, and you would do like git clone, and then you would clone the repository and if you want to do this, you can, but it is a very big repository, so it would take a long time. Um, so yeah, if you went here and cloned it, yeah. So git clone, and then you would just use the HTTP target. It would bring it all in into a folder called Blender. And so I'll show you where I have done that. So I put it inside this other folder called Blender Git because that's what they say to do in those instructions. And so you'll see I have a folder in here called Blender. And so this is the whole all the source files like you saw in the Git repository. And then we can look. I've made another folder called build because they want you to compile it and configure it inside of this folder to keep everything clean. And then so what we can do is just use that command that they gave us, and then this would do all the configuration. And so you'll see as we do this, it's saying we found this Visual Studio 2022, and that's what it's going to use. And that's really important for how they set it up, their CMake files, because we'll get into it later why it matters which compiler you use. But if you try to use like the WebKit uh, thing that I recommended, it won't work because essentially they've already compiled some of their stuff as using Visual Studio because they're assuming that's what you're going to use since you're on Windows. It would, of course, be different if you're on a different operating system. So yeah, it's already configured the project. You can see here, it says configuring done. And then um, it's going to generate some files and some other stuff before it's completely done. So any questions on this while we're waiting? So this is actually the quicker part. The part that takes longer is all the compiling, and it takes up a lot of space in your computer. This laptop's pretty old. I only have like 250 gigabytes, so like every bit of space counts. And I was testing this out. I ran out of space really fast. So so yeah, this part specifically right here, where it's passing the configuration or using the configuration file that's from bpy module.cmake. That's going to make it so that it compiles into a Blender or a Python module. So Chin, do you use Python ever?
Uh, yeah, yeah, a little bit.
A
Yeah.
little bit.
I,
So you know how they do like their packages through like the modules and things like that, like NumPy or something.
just a very little bit. Yeah, I did mostly C++.
Okay.
Yeah, I kind of get what you're doing right
Hmm. Okay, so now it took a long time to generate all those files, and we can actually look at everything it generated. And it's a lot. And you'll see these like special file extensions, like, and that's how you know that it's done through Visual Studio. And whenever you do it using like the Linux version where you have make files, it's a lot cleaner. There's a lot less files that come up. But it's just differences in how they wanted to do things. So now what you could do is do to actually compile it, you do CMake build, and then this would start based on all the configuring that you did. When you configured everything, it found all the necessary pieces to actually compile it. And if you don't have those pieces, it'll tell you, oh, you're missing this library or something like that. And you'd have to go and fix that. So now everything's set up to compile, and that would take a long time. So we're not going to do it. So this is as far as we'll go. This is kind of what you need to do to, yeah, compile Blender as a Python module. And we'll go back to, so before we get into how we can use CMake, we're going to do some things without CMake just to see, like, kind of get an idea where the pain points would be without CMake and then understand why it's useful. So we're just going to make a simple program that does dot products of two vectors. And this was supposed to render as math. So it's going to be two vectors multiplying each other. The vectors are like 1, 2, 3, and 2, 4, 6. And so their dot product is going to be 28. So that's an answer we're going to be looking for a lot during this workshop. But we're going to start. And were you guys able to clone the repository, or are you guys kind of going to do it from scratch? Either way, if you're in your initial folder, like that you're gonna do this stuff in, I guess I would suggest like make a clean empty folder. Uh, we'll start by making a folder called simple. So you can do like just create a new folder, do like make dir simple. Um, and then inside of that, make a file called fun math, or you can name it whatever. Really, I call it funmath.cpp. So we can take a look at what this is. So the CMake list will be for later, but this is what we're gonna make it first. And so first we'll define our main function, and then um, we're gonna make two vectors, uh, kind of like I guess like that dynamic way. I'm not the best C plus. I won't pretend to be the best C++ programmer, but it works. So we're gonna go with it. And then like we'll declare the two vectors and then we'll instantiate them. And so this is the very clever formula that I made to make our vectors, and that's why they are what they are. I just did one and then one times two. Um, and then we'll create a function called dot product. So I'll let you guys, if you guys are writing this out yourselves, I'll let you guys catch up to this. But yeah, there's basically two parts we covered so far. Just like allocating, and I guess we're also instantiating the length, but then also allocating these two vectors. And then also, yeah, and then also, yeah, you have to return 0. So that's going to be a requirement at the end of it, just so you know your function or the main program runs without failure. So then we'll make a simple function to do the dot product. And the reason we're doing it in a function is just because we're going to make like the function into a library later. To just see, because like that's where the complexity really starts to come into it, is when you start, separating your code into multiple files, and then maybe those files are from another library, and you have to just find some way to bring them all together. So I'll make a function called dot product. It's going to take 3 arguments, two like vector arrays, um, and then the length of each of those vectors. So it's just iterating over each of the indices of the arrays and then adding them up like a dot product. And then we'll want to see a result so that we know that it's being computed correctly. Okay, so that, and then of course return 0. So that is the gist of our simple program that we're going to do. And now we're going to compile it the basic way. So if you have the the emulator on Windows, you can do it like this. And also if you have it, if you have Linux or Mac, this is probably also a really simple way to do it. And so, but this is like the GNU compiler. So we're going to use G++, and then the path to the simple version of the fun math file, and then we're just going to name it the executable that's produced from it, fun math. So I'm in the folder above the simple folder still. So that's where this command works, because it's calling into it. So we'll compile that. And so this is like on that first slide I showed, you can just compile it simply because we just have one file to do. And then we can run it, and we get 28. That's what we expected. So that's simple. So now let's say we have a ton of functions and we want to separate them into their individual files to like sort of contain them to make our library more readable, for example. And so now we have uh, other files that we need to also incorporate into our compilation. So to sort of simulate this, we're going to take our dot product function and we're going to put it into its own file. And so when we do this, we also need to make a header file. We don't need to make a header file, but we're going to make a header file so that that the compiler knows that in our main function, like what this dot product function is supposed to look like. And so we're going to create a new folder called external func, and then we're going to copy our other files into it, and then make a new file called dot product cpp, then copy the dot product function into it. So our old main function into like copy the old main function into the new file as well and name it fun math. And then instead of, you could name it fun math again, but I named it fun math lib. So I'll just show you guys what this looks like. So we're in our main folder still, and I'll remove our fun math, our old executable, because we're going to make a new one. And then let's look at the external func. So we have fun math. You could just name it fun math again, but I have it fun math lib, and then also dot product dot cpp. So if we look at the dot product, what's in the dot product file, it's just our dot product function. And if we look at what's in fun math lib, we'll see that it's just the main function. So everything's been separated out. So here, yeah, I guess were you guys able to, if you guys were following, were you guys able to compile it and everything?
I haven't been doing it on my own. I just watching you.
Okay, yeah. No worries. Yeah, if you guys have any troubles, or I guess I should say, if you guys have had any troubles compiling it, let me know.
I need
Okay.
a while.
Yeah, yeah. Yeah, we'll take a minute. Okay, so yeah, if you've copied the files over into the new folder and split them up, you should have something that looks like this. But like I said, we also need to make a header file so that this main file we have here knows what this function will look like without having to like have it explicitly defined in there. And so that's what this looks like inside of the header file. So we have .pod HPP, and then the only line in the file will be like this. So this is going to be like the signature for the function. Then in our main file, we just add another line to say, we add at the top, probably like right here, and we just say to include this header file. So now we can compile both of our files, our CPP files that we made, and yeah, we'll get our same executable, hopefully. That's the idea. So now we've recompiled based on our new sort of project directory setup, which is just making one file into two. And if we run it, we still get the same answer and there's no errors. So everything is working great. So you'll see that this command that we used to compile it, we had to like type out each of the files we wanted individually, and you can see how this could become complicated once you have many files. Although I'm sure there's some like syntax you could use to like get all files ending in CPP or something like that. But I'm sure there's other arguments to be made on why this can become cumbersome and why you would want to use configure and build system. Um, so yeah, now we'll go into our next stage. So this is like increasing levels of complexity. We had something simple, we made it a little more complicated, and now we're going to make it even more complicated. So there's this idea of a library. So you can compile things and you can make executables and you can run them, or you can compile things and you can make them into libraries. And these libraries are going to contain all the binaries for certain functions that are defined once again by header files. And so one of the libraries that I talked about was BLOS. And so BLOS contains linear algebra subroutines, like matrix multiplication. I'm not sure what else. That's all I've used it for. But so instead of writing our own dot product, like in our function that we've made, we could use a BLOS library. So the BLOS library is actually too big for me as well, like storage wise. So we're just going to make our own library instead of using the BLOS library. And so we can do this simply if like I don't know how you do it necessarily on like using the Visual Studio thing, but through the sort of emulator thing I talked about in the beginning, the Web64 dev kit, you can use this command called archive to make a library. So first though, we're going to set up our new like file structure in a new folder called library. So yeah, we'll look at that, what that looks like. So, we've done simple, we've done external function. Now we'll look at library. So in here, we're gonna start off with all the same files. We're gonna start off with .prod.cpp and funmath.cpp and the header file, the HPP file. So we'll look at funmath, what that looks like, just to make sure nothing changed on us. So this is looking the same. We still got our header file in here, and then we're just calling the dot product function. And then if we look at this is, if we look at the dot product CPP, this is still looking the same. And then we can look at our header file as well. And then that's very simple. So that's all you should have at the very beginning. And then we're going to make our library file. And so it's kind of I'm not really sure how it's typically done, like for like big projects. But I think the way it usually works, especially like a HPC, is like you'll have a certain directory from like the root directory where there's a bunch of libraries stored. And so like I know if you use the Great Lakes thing, you'll use modules to load in different libraries. So you can use module load OpenBLOS, and then it'll put a library file in your directory somewhere, like one we're about to make. And then CMAKE just knows where to find that. But we'll get into that later. But anyways, just yeah, kind of context for how these library files are actually used. And these are going to be static libraries as well. I guess I should mention there's also dynamic libraries. And on Windows, those are the DLL extensions. And there's a bunch of differences, but we won't get into them. Okay, so now let's go ahead and make our library file. Chin, how are we doing? Okay. Okay, so what we're going to do is not this function because there's a typo, but we're going to run this and with the O here. And this is going to, I talked about before, you can like compile to make it executable, or you can compile. This is not really compile to make a library, but this is compiling to make an object file. And so we're only compiling here, and we're not linking. And so that's what the -c argument means. And so the output is going to be .product.o, and that is our object file. So we'll run this. And so if we look in our, I guess in our library thing, I already had the .product.o, but so if I remove that, so you'll see it's not in there. And then by compiling, but using the -c argument, we'll get our object file. And I'm pretty sure this is the object file is still in assembly code. And then once you link, I think the linking turns it into binary. I think that's right. So yeah, now looking in here, we have our dot product and I'll get rid of our library file as well, so I can show you guys how, just to prove that that's working. So library file gone, and then if you have this sort of like emulator, you can use this command, and then the RVS I think is some arguments to say that you want to make this library file. So this is going to be the output. This first argument, this is going to be the input. So this is like if you had more of these object files you wanted to make into a library, you just, I think, add them on into this command. So yeah, now this has been produced. Oops. Here. So how do we compile with a library? There's two things you need to specify. I think where to look for library files, and then usually you can just say the name of the library. But whenever I just say .prod, it gives me an error saying you need to have lib in front of it or else put this .a on the end. But anyways, this is the full command for the compiler to make your new executable, but incorporating the dot product function as a library. So, so before we had two C++ files, now we have one C++ file and a library. So this is like kind of way to condense all those extra files we might have. So we have a new fun math program, and it's still giving us the same answer. Still working without any errors or anything like that. So if you want to use many libraries, you get into this problem again. It's like, how are they all managed? And do those libraries themselves need to be configured? And that leads into more complications. So that's that's what I'm trying to say. CMake is going to make a lot of these things easier. So now we're going to do all those steps again, but by using CMake. And the way that CMake works is always through these. I mean, I'm sure there's other things, but the basics of it is it always uses the CMake list.txt file. And these are going to be the instructions for what CMake should do. So first we'll start out back in our simple folder, and we'll make a CMake list.txt file in that simple folder. And then there are three main things you need in your CMake list.txt in order for it to work. And so you have to say what the CMake version, the minimum is, and then you also have to name your project and define some things about it, such as its like version number. And then you have to tell it what executables to compile. And these are called targets. And the target I don't know if they're always end up being executables, but that's what's gonna happen for this target, funmath. So we'll get our funmath.exe by compiling funmath.cpp. So we go back to our this is in our simple folder. We have a build folder in here. That's interesting. But we have I think Visual Studio Code did that, because if it finds a CMake file, it'll like think, oh, you want to build this project, and it does it. We'll just delete that. So we know it works though. That's good. So yeah, setting the CMake minimum required, adding the project, and then adding the executable. And you don't have to specify the languages that you're going to use. Okay, it's trying to configure it again. It's dedicated. You don't have to specify the language that you're going to use, but since we are only using C++ in this, we're going to. Oh no, it did fail. Okay. Anyways, yeah. So then, like, what you want to do at this point is going to vary by kind of preference, but you could just do CMake and then you have to specify the folder that has the CMake list.txt file in it. So we would, for our case, we would say simple. And then this would then dump a bunch of files into our main directory right here. And it, like you saw how it was for the Blender thing, a lot of files are generated. So what we're going to do instead is we're going to make a folder called build to kind of keep everything nice and organized. So I don't know if I have anything in here. Yeah, so this is empty. And this is where we're going to dump all those files that CMake is going to create. So to run our set of instructions we made in our CMake list.txt, you just do CMake, and then the path to the where the top level CMake list.txt file is. So it would be dot dot to go one level up, and then simple to go to that actual directory.
Is there supposed to be an enter in the line above where you're at?
Yes, thank you. uh, yeah, let's try that again. Okay. Sam to the rescue. So now you see it's going to start configuring it, and it's going to use the Visual Studio stuff because I think that's just what it defaults to on Windows. But you'll see later we're going to specify something different. So configured and it generated everything. And now if you were using Linux or the like Makefile build system, you could just type in make in this and it would run everything. But we're using Visual Studio Code, and to build in that, I think you usually have to go through Visual Studio Code. So one thing that CMake also provides is a build system. So you can do CMake, you can either do this through Visual Studio Code or you can do CMake and then build, like I was saying for the Blender library earlier. And so this is going to do the building of the project, making our executable. So now you see we have, all these files were created by our configuring, and then it put the actual executable in this debug folder because, yeah, there's a lot more to set up with Visual Studio Code, but I think by default it does this debug build version. So we can do debug, and then our executable will be in here, and we'll get the same answer. So looking at debug, we see our executable. And so at this point, you could do a bunch of other things to configure for project. And so yeah, here's some of the commands that we ran. We can, like I have in the current file, you can set the standard of C++ you want to use. So if there's certain features in C++11 and you want those to be, like you don't want anyone to have trouble with that, you could specify that in your CMake, and then or potentially you could hard code a compiler to use, but there is problems with doing this because your path to your compiler might be different to someone else who's using your project. Okay, so that was the CMake equivalent for the simple example, and which is arguably more complicated than just using the compiler. So it's like now, like when should you use CMake? That's kind of the thing you might be thinking about. So now we're going to use it for more complex examples and see. I mean, probably none of these are going to be complex enough to warrant using CMake, but for illustrative purposes, they're good. So we're going to go back into our main directory and look at, we're going to look at the CMake files for the external func CMake. So copy your current CMake file into the external func folder. And then we're going to make some modifications to that so that it configures and compiles everything correctly. So we have all these extra files that are doing stuff, but they're not part of like our main executables. And so we can also kind of consider those as libraries that are going to be like compiled separately. And so by adding the extra instructions we're going to, I think it actually does make these separate sets of scripts into actual like library files. So the first thing that we're going to do is we're going to say we're going to make a dot product library out of just this dot product.cpp script. And then to associate that library with our main project, we're going to use this target linked libraries function. So the first argument is going to be it's either the project or the target, but we named them both fun math. So fun math would be the first argument, and then dot product is going to be our library that we want to link during the linking stage. And then also now, so in our simple example, we didn't have a header, but now we do have a header, and we want to include it into make sure it's included when we do our compiling. And so for this purpose, the target include directories function. So for this, yeah, once again, you're typing in, I'm not sure if it's either the project name or the target for the add executable. But yeah, for fun math, we're going to include all the header files and that are in the project source directory. So for the project source directory, that would be external. That would just be any header file that is in this directory. And yeah, so this is all we need to add for CMake to run in this example. So in our build folder, we can get rid of everything. Just to, yeah, you would want to get rid of everything because we're now like essentially configuring a different project since it's like a different folder, a different CMake lists and everything like that. But we can just do CMake and then the path to the CMake list.txt. And the configuration went well. And then we can do CMake build. And then we can run it again, and it's still going to be in the debug folder if you're using Visual Studio Code or Visual Studio to their compilers to compile. And so we still get 28. Okay. Finally, to the last analogy or like CMake equivalent of our example. So now we have the script files, like the source code, and we can make that into a library. But what if there's already a library that exists and we want to incorporate that? Like we don't have the source code, it's already been compiled to the object files, but we want to still want to include the functionality of that library in our project. So this is kind of a rare example because like the way you usually find libraries is with this. There's a special command called find package, yeah. And like I was saying, there's certain directories in your like in an HPC configuration. There's certain directories that are going to have all these packages, and so you just say that like, okay, all the packages that I would ever use are going to be in this directory, and then you use this find package command, and it would find that package for you, and it would include it. And then the other example is where you just have the raw source code anyways, and you could do it like in the above example right here. But this is kind of like, I think a lot of the people who work on CMake, they say don't do it, don't do this sort of thing. If you have to do it, do it some other way. But this is going to be like a good illustration of, I guess, how it would work otherwise, and it actually shows something good about something important about the like keeping your compiler consistent. So like if a library is compiled with a certain compiler and you want to use it in your project, you also have to use that same compiler, or else the linking might not happen correctly. Yeah, okay. So copy that same CMake list.txt into our library folder. So we have our CMake list.txt and library, and we're going to look at it. So there's going to be a few things different in here. So what we're going to change is we're going to add this line, target link libraries. So before we did target link libraries, we had fun math here, but then we just had the name of our library that we already created. So this is what we had before. We created a library called dot product, and then we were able to use that in target link libraries. Now, instead of using like this variable name that we defined previously in our instructions, we're just going to point to the location of this .a library that we made previously. So before we can run this, there's a catch, and it has to do with like keeping your compilers consistent, like I said. So if you remember, when we made this .a library, we did so using like the GNU emulated compilers. And so what we've been doing with CMake so far is that we've been using the Visual Studio compiler. So I'll go ahead and show you what happens when we try to use different compilers in different parts of this process. Oops. So our build directory is clean, and we're going to do CMake library, and then we're going to, we'll just run it like that. And so this is what we've been doing pretty much for all the other examples. And so you see it's starting to use Visual Studio Code, and we're getting compiling stuff. So the configuration works fine. So now let's actually try to build it like we have been doing. And so this is where it actually gets to the linking part. And so what happens is we get a linker error because our library has a certain name and it's assembly code for this function. And when we compile it with our Visual Studio compiler, it's looking for a different name because the Visual Studio compiler and the GNU compiler name stuff differently. I think that's what's happening. So when we use these different compilers, it's not able to link the function correctly. So what we can do to fix this is we can specify, you can specify the type of compiler using explicitly, but it's not going to help. In my case, when I was figuring this out, it didn't help to just specify compiler. You also want to specify the the type of build system that you're going to use. And so by specifying the type of build system we're going to use, we also are specifying the type of compiler we use. So min.gw is this set of emulators for the GNU stuff. So I think it's like minimum GNU for Windows or something like that. And so that's what we have, and we're going to use that. If you have some other type of emulator for these things, you would have to use a different type of make files. But by doing this, we're going to configure our project to use the same type of compiler that we used for to make our library file in the first place. Oh, okay, so yeah, make sure you remove everything that you previously did with Visual Studio. Okay, and then here's another thing that's happening. So Windows, when like CMake is doing this stuff on Windows and you're using this emulated thing, it's thinking like CMake is copying certain executables. And when your computer sees executables being copied, it thinks that you're getting a virus. And I have my notifications silenced right now, but yeah, so threats found right now. And so it thinks it was a virus. So it deleted some stuff while CMake was doing its things, and that's why we're getting all these errors. Sometimes you can just compile it, like configure it again, and it'll work fine, like it did in this case. But other times, like I tried to doing this with Blender, and it was a different story. But I think there are some, probably if you're on Windows, you should use Visual Studio for everything. But in the case that you're, have some special project using GNU stuff, you probably have to find a workaround for this. Okay, so we have our thing configured, and now I can show you guys what it's like to use like the Makefile system instead of the Visual Studio. So we've just configured. And if you remember when we configured with the Visual Studio stuff, we had tons of files. And so this is what I mean whenever you're using the Makefile build system. So we just have one Makefile here that's going to give instructions essentially for how to compile everything. So if we just run make now, it's going to build our program. And it has a really cool way of doing it too. It's like nice percentages and stuff, and yeah, colors. So now Fun Math has been built too, and it's not in the debug folder like it was for Visual Studio. It's just inside of the same directory that our makefile was in. So we run this too, and we get 28. Okay, so we have a little bit left to go. Any questions, comments, or concerns? Okay, so this is as far as I've ever used CMake. And you can actually, so we've use CMake to pretty much change like what files are going to be compiled, but you can also use CMake to change the functionality of your files. And you can do this. The main reason that I've done this is to say, like, if you haven't found a certain package, like say we're trying to use BLOS for something, and you tell CMake to find BLOS somewhere in the operating system, but it can't be found. In that case, you couldn't count on BLOS for the dot product, for example, let's say. So you also written your own dot product. That's less efficient, but will work in the case that BLOS isn't found. So in the case that you can't find BLOS, you want to have sort of a backup in your compilation that would use your own like handwritten dot product function instead. So this is kind of we don't have any like examples of this, but this is kind of how it would work. So first you'd use the find package command like I was mentioning earlier, and you would just say BLOS. And then what this find package command does is it creates a variable called BLOS found, and it'll either be true or false. And then based on if it's true or false, you would use this command called add compile definitions. And so what this does is it creates a variable inside of your like C++ environment that you can then call. So this would be then used in our source code or headers. So you say if BLOS is found, you would include the header for CBLOS, but if it's not found, you would include your header for your own custom written dot product function. And then so you'd also need to have similar branching statements in your code where you call the function, or you just have both functions use the same interface. Okay. So that is it for our workshop. Any closing questions?
I guess all the issues I've had with CMake is someone describes on their GitHub how to use CMake to build their thing, and then I go to use it and it throws a bunch of errors.
Yeah.
And it's like an old repository from like years ago that they don't maintain anymore. So it's like something's gone wrong between when they posted the instructions and now.
Yeah.
So it's like I never know how to debug that.
Right.
But it's good to actually understand more about what it's doing.
Right. Yeah, I think I mean I don't have extensive experience, but I think the most experience I had is like I use CMake for my own project to just make like compiling it easier. But I know from the scientific computing class that I took, mainly when you have problems with CMake, it's because like you're missing a library or like you're not using the same compiler that there's it's a problem with like your environment rather than like maybe, and it could be like the CMake version as well or something like that. But yeah, yeah, like I think they also said in the scientific computing class that that's like the worst type of errors to get when you're trying to use someone else's software. But yeah, I hope you guys found this educational and interesting as well. Yeah, thanks for your time. We just have a few more announcements left for the meeting, and then we'll be over.